Today we'll study about traveling salesman problem. So in traveling salesman problem we have a salesman and there are n cities. So we have one salesman and there are n cities. Cities are numbered from 1 to n. 1 to up to n, and we have distance between the cities, distances. So from city I to city j, we have a distance, we call it Cij, and between any pair we have a distance. So we consider all possible pairs of the cities and we represent this as a complete graph of n vertices, Kn. So Kn is a complete graph of n vertices and this is weighted graph. Now we can have two possibilities for this graph. So the distances can be two-way or one-way. So there are two possibilities: two-way traffic or one-way. So two-way means it is symmetrical. Distance from I to j is same as distance from j to I. One way means this may not be true. Distance from city I to city j may not be same as distance from city j to city I. So we have a weighted complete graph Kn, and the salesman will start from city 1, and has to visit all other vertices. The remaining cities number 2 to n and come back to 1. So cities are there 2, 3 and so on up to n minus 1 and n. So visit them in some order, something like this, and finally come back to city 1. So the total distance traveled we have to minimize. So our objective is minimize the total distance traveled. This is our objective. So this problem is called traveling salesman problem. In short, we can call it TSP. Traveling salesman problem. In short, TSP. So first we'll see what is the time complexity and space complexity for the brute force algorithm. So brute force algorithm, what we do is simply enumerate over all possible tours and find the minimum. So first we analyze the brute force algorithm for TSP. Brute force algorithm for TSP. So here what we do is simply enumerate all possible all possible cycles of length. Here better we call simple cycles. Simple cycle means no city is repeated. Simple cycles of length n. Just enumerate and find the total distance traveled and minimize it. So this is the brute force algorithm. Now how many possible cycles of length n we can have? So we have to compute the number of cyclic permutations. Compute the number of cyclic permutations of size n. This is easy to compute. So for linear permutations we have n factorial. So we have n factorial linear permutations. So we have to count the number of cyclic permutations. It is very simple. Take any cyclic permutation. The simplest example we can take this 1, 2, continue in this order 3 and so on up to n minus 1 n, like this 1 2 3 in order n 1. So there are n linear, so we can easily observe that n linear permutations they map to a single cyclic permutation. They map to a single one cyclic permutation. How we can easily see? So first linear permutation we can start from 1, 2, 3 and so on up to n and back to 1. This is 1. Second we start from second 2, 3 n 1 2. Third one start from 3 and so on, return back to 3. Same way continue up to nth linear permutation, start from n 1 2 and so on, n minus 1 to n. So there are n total linear permutation, they correspond to a single cyclic permutation. So to compute the number of cyclic permutations, simply divide the number of linear permutations with n. So number of cyclic permutations we get cyclic permutations is simply divided by n. Number of linear permutations of size n. N factorial, number of linear permutations divided by n, we get this as n minus 1 factorial. So these are number of cyclic permutations. Now we compute. So given a single cyclic permutation, what we have to do is find total distance traveled. So for total distance traveled, we have to just add for total distance traveled. We have to add n distances, and for adding n distances we require n minus 1 additions. So this will require n minus 1 additions. In addition to the n minus 1 additions, we also require a single comparison to keep track of the minimum. So one comparison is also required. Comparison like this to keep track of the minimum. So total operations for a single n cycle is n operations. Are required. So now we can easily find the time complexity. We can write T1n is equal to, there are n operations per cycle and we have n minus 1 factorial possible cycles. We get n factorial time complexity. So we can easily write this in big theta notation as big theta of n factorial. Now for space complexity, we by S1n we denote the space complexity of the brute force algorithm. So it is only big theta of n, because we need to keep we should have space for storing the n cycles in n space and some constant number of additional space required for some auxiliary variables. So big theta of n we get as the space complexity. Now next we'll design a dynamic programming algorithm for the same problem, and where its time complexity will be decreased and space complexity will be increased. So it will be a time space trade-off. For saving time, we'll spend our space. Dynamic programming algorithm for TSP. So dynamic programming algorithm, what will happen? It will reduce the time complexity, but it will increase the space complexity, because we have to keep track of the sub problems. So we'll get a time space trade-off. Here we will see a time space trade-off for TSP. Time space trade-off. For TSP. So time space trade-off means to save time we have to expend more on space. So now we'll design a dynamic programming algorithm for TSP. So first we should determine the optimal substructure of TSP. So the original problem, we have to express the solution of the original problem in terms of the solution of the sub problems, and we will have overlapping sub problems. We'll avoid solving the sub problems more than once to save our time complexity, and to keep track of the sub problems, space complexity will increase. So we'll find first we'll determine optimal substructure of TSP. Optimal substructure of TSP. So here we formulate our problem. We make a function g. GIS. So here I is the start city and S is a set of intermediate cities. It is something like this. Traveler will start from I, move the cities within S and come back to city 1. So this S excludes these two, city 1 and city I. So here our requirement is S is a subset of v minus 1 and I, where v is the set of all cities, p is equal to 1 up to n. So the intermediate cities except they exclude city 1 and city I. So traveler starts from city I and tours through the cities in S, intermediate cities in S, comes back to I, comes back to 1. So the total distance traveled we denote by GIS. Now how we can find GIS? So first we consider the original problem, and the idea is very similar. It also applies to the general GIS. So the original subproblem is original problem, not subproblem. Original problem is G1 V minus 1. Starting from city 1, we have to move all other cities except for 1, come back to 1. So now we can see our traveler starts at city 1. Now what is the next step? So we can have n minus 1 possibilities. For the next step, traveler can choose city 2, 3 and so on. In general, city I up to city n. These are n minus 1 possibilities like this. Now we also note what is the cost of going from city 1 to city 2 is C12, similarly C13 and so on. In general, C1I up to C1n. So once the traveler is at city 2, now how much cost it will take to travel the remaining vertices and coming back to 1. So it is precisely G2 V minus 1 2. Similarly we can write for others also. For 3 it will be G3 V minus 1 3, and in general it will be for I GI V minus 1I, and for n it will be G n V minus 1n. So now we can write. So the cost is simply add. For example, if the traveler chooses 2, then C12 plus G2 V minus 1 2. So just we have to take the minimum. So we get the recurrence relation from this observation that G of 1 V minus 1 is equal to minimum. I ranges from 2 to n, 1 to I cost plus G I V minus 1I. So this is recurrence relation for the original problem. Now exactly same idea will apply for general GIS. Exactly same structure, and we can write this for a general I and S. Same thing we can write GIS is equal to minimum. J is from S. From I, if we go to J, cost is Cij plus the remaining subproblem is Gj S minus J. So this is recurrence for general I and S. So now here our observation is that the size of the subproblem. So the original problem is of size number of elements in S. The sub problem has size one less than the original problem. So our original problem depends on sub problems of size one less. So here we follow the bottom up approach. We start with the smallest sub problem. So we start with in increasing order of size of S. So we start with first empty set. Number of elements in S is 0. Next we increase this to 1 and so on up to this point, and n minus 1. This goes up to n minus 1. So we follow the bottom up approach in our dynamic programming. So I will write the algorithm, then we will find its time and space complexity. So first I will write the algorithm. Call it TSP. Input is the set of vertices V and the cost matrix, the adjacency matrix, and cross n matrix. So first we solve the smallest sub problem for I is equal to 2 to n. So smallest sub problem is GI phi, empty set. So GI phi means we are starting at city I. Traveler starts from city I. Now there is no intermediate city, go directly to city 1. So the cost involved is CI1. So we initialize it to CI1. So this is the smallest sub problem and its solution is trivial. Next we solve the next level of problems of sizes starting from 1. So next we have a for loop. For loop k is equal to 1 to n minus 2. So actually we have to find up to n minus 1, but for n minus 1 only a single value is required. So we'll find it separately. Now for I equal to, we have to find the values from I equal to 2 to n. So k is fixed, k is the size of the subset. So k, we can write size of the subset is k, and I ranges from 2 to n. So given I and size of the subset, we simply choose all possible subsets of size k. So we have for all loop for all subset S, which is a subset of V minus 1i. So we exclude 1 and I because 1 is our final destination, I is our start destination, and intermediate cities are in S. So for all S, which is a subset of V minus 1i with size of the subset S is k. So now we simply apply the recurrence GIS, the same recurrence formula. Apply the minimum, J is in S, Cij cost plus G J S minus J S minus J. So now we have computed all subproblems. Now we have to compute the original subproblem. So we compute it separately using a separate recurrence, similar recurrence. Why separate? Because we have to find only G1 V minus 1. So here I, we have to take only one. We are not interested in starting from any other city. We are interested in only starting from city 1. So we find a single solution, G1 V minus 1. Again very similar formula. Minimum I ranges from 2 to n, C1I plus G I V minus 1I, and finally we return our value. Return G1 V minus 1. So this is our dynamic programming algorithm. Now we'll find its time complexity. So for each step we find the number of executions and sum. So the main contribution for time complexity will come from this triple for loop. Rest are minor contributions. So first lines 1 and 2 we compute, it runs for n minus 1 times. So line 6 we consider. So for line 6 we have this for all loop. The for all loop. So first so here line 6, if we consider minimum over j in S, so there are k possibilities. There are k values we are considering of Cij, and we have to add, and we have to find the minimum. So these values are already in the table. We consult this, and this is given as the input. We consult these two values and then add it for k number of times, because size of the set S is k, and then we find the minimum. So two operations we have to do. First we have to add, and then second is we have to keep track of the minimum. So two steps are required, and for a total of k times. So this step 6 will take in total 2k times. And if we consider the for all loop 5, so here we have n minus 2 vertices, and we have to choose k vertices. So this takes n minus 2 choose k possibilities, and line 4 is executed n minus 1 times. This n minus 1 times. So next we consider line 7, and so again line 7 it is very similar. It will take time 2n minus 1. n minus 1 times. Now we add everything. this line 8 will take only a single time. So just add everything and get the result. So we write the expression for our time complexity, call it T2n is equal to, adding everything we get this as n minus 1 plus, so this n minus 1 comes from this lines 1 and 2. Then we have this summation, sum of all k is equal to 1 to n minus 2, n minus 1, n minus 2 choose k, 2k. So how this comes? This 2k is complexity of line 6, n minus 2 choose k is for line 5, n minus 1, n minus 1 is this line 4, and the summation is from k equal to 1 to n minus 2, k is equal to 1 to n minus 2 plus 2n minus 1, this is for line 7, and line 8 is 1. Now we simplify this expression. This is equal to, we write this as 3n minus 2, we just simplify it, 3n minus 2, adding the separate terms plus, so 2n minus 1 plus n minus 1 is 3n minus 2, and here we take 2n minus 1 out, factor it out and write 2n minus 1 summation of k is equal to 1 to n minus 2 n minus 2 choose k multiplied by k. Now we expand the binomial coefficient in factorials to further simplify it, and write this as, this is equal to 3n minus 2 plus 2n minus 1 summation of k is equal to 1 to n minus 2 k multiplied by n minus 2 factorial divided by k factorial n minus 2 minus k factorial. Now we further simplify this. So what we do is we cancel this k, here it becomes k minus 1 factorial, and we take n minus 2 out to further simplify it, and we write this as 3n minus 2 plus 2 n minus 1 n minus 2 summation of k is equal to 1 to n minus 2 n minus 3 factorial divided by k minus 1 factorial and n minus 2 minus k factorial we rewrite in terms of n minus 3 and k minus 1. So we write this as multiplied by n minus 3 minus k minus 1 factorial. So this way it becomes a binomial coefficient n minus 3 choose k. So we further rewrite this as 3n minus 2 plus 2n minus 1 n minus 2 summation of all k is equal to 1 to n minus 2 n minus n minus 3 n minus 3 choose k minus 1. So again we rewrite, just a very simple change of variable we make. So we introduce k prime equal to k minus 1. So just use k prime equal to k minus 1. So as k varies from 1 to n minus 2, k prime will vary from 0 to n minus 3. So writing in terms of k prime, we get this as the same thing, 3n minus 2 plus 2 n minus 1 n minus 2 summation of all k prime is equal to 0 to n minus 3. n minus 3 choose k prime, n minus 3 choose k prime. So this sum is exactly 2 to the power n minus 3. So further we simplify this as three n minus 2 plus 2n minus 1 n minus 2 2 to the power n minus 3. So again we are not interested in finding the exact time complexity. Again just simplify this as plus n minus 1 n minus 2 2 to the power n minus 2. So again we are not interested in finding the exact time complexity, just in asymptotic notation. So you can easily see this is the contributing term. Here it is asymptotic to n square, this is asymptotic to n 2 to the power n. So this becomes big theta of n square 2 to the power n. So this is the time complexity of our dynamic programming algorithm. Now just compare this with big theta of n factorial. So using Stirling's approximation, we use Stirling's approximation for n factorial. So it becomes big theta of for comparison square root of 2 pi n n by e to the power n. So now we can compare. So this is much less than the brute force algorithm. Just for easy comparison, just take log on both sides. So here this becomes log with base, we can take base 2 or e, take any base n, 2 log n with base 2 plus n. Compare this with log at the right side, half log 2 pi plus half log n plus n log n minus n log e. So just for comparison, the two quantities, here the dominating term is n on the left side, on the right side dominating term is n log n. So for sufficiently large n, this right side dominates. So time complexity of brute force algorithm is much higher than time complexity of the dynamic programming algorithm. Now we find the space complexity, and we'll see that space complexity is also exponential. So space complexity, it is easy to find, S2n. So space complexity is simply the number of subproblems. Just count the number of subproblems. We have to store them. GIS, all GIS such that S is a subset of V minus 1I. S is a subset of G, and also this for I ranges from 2 to n, plus the original problem, which is 1. The original problem is G1S, G1 V minus 1. So now we can easily find the sum. This is equal to 1 plus sum equal to k varies from 0 to n minus 2, the size of the subset S. I ranges from 2 to n, so n minus 1 multiplied by V minus 1 to I. So there are n minus 2 vertices, and we have to choose k out of n minus 2. So again, this is easy to find. 1 plus sum of all k 0 to n minus 1. Just take n minus 1 out, n minus 2, choose k. So this becomes 2 to the power n minus 2. We get 1 plus n minus 1, 2 to the power n minus 2. So again, we are not interested in finding exact space complexity. In big theta notation, this is big theta of n 2 to the power n. Now just compare this with space complexity of brute force algorithm. It was only linear. So we are getting a time space trade-off. We are trading time for space. To save space, we expend more on to save time, we expend more on space. And here we can also optimize this because we can reuse the space. So there is no need to store all subproblems. Only requirement is just use the space for one level of subproblem, find the solution to the other level, and then reuse the space. So we can optimize this also, but again it will come to be exponential. So we'll not go into the detail of optimized space storage. Just know that it is exponential. So now we take a very simple example of how to execute this dynamic programming algorithm to solve the traveling salesman problem. So a very simple graph we'll take of 4 cities. Take this graph 2, 3, 4, 1, 2 to 3 cost is 4, 3 to 4 cost is 5, 4 to 1 cost is 2, 1 to 2 cost is 1, 1 to 3 cost is 3, and 2 to 4 cost is 6. So now we'll solve this problem. So we follow the bottom up approach. We start with the smallest subproblem of size 0, which is trivial. So first we find G2 phi. Smallest level we have G2 phi, G3 phi, G4 phi, 3 smallest subproblems. So 2 phi is direct distance from 2 to 1. it is 1. Next is 3 for G35, 3 to 1 direct distance is 3, and 4 to 5, 4 to 1 direct distance is 2. So we get these values. Next level we have subset S of size 1. So there are 6 possibilities. First is G23. So we write its expression 2 to 3 cost. 2 to 3 cost is 4. 4 plus, we move to 3. So we write G3. The remaining element after removing 3 is 5. G3 5 we know is 3. We get the value 7. Same way we compute G24. G24 is 2 to 4 distance. 2 to 4 distance is 6. We move to 4. Remaining set is 5. G45 is 2. We get the value 8. Next is G32. G32 is first 3 to 2 distance. 3 to 2 distance is 4 plus G. We move to 2. Remaining subset is 5. G25. G25 is 1. We get the value 5. Next is G34. G34, we find the value 3 4. 3 to 4 cost is 5. We move to 4. Remaining subset is 5. G45. G45 is 2. We get the value 7. Next is G42. So 4 to 2 value. 4 to 2 value is 6. We move to 2 and set remaining is 5. G25 value. G25 value is 1. 6 plus 1 we get 7. Now last value is G43. G4 3. 4 to 3 value. 4 to 3 cost is 5. 5 plus G. We move to 3. Set remaining is 5. 5 plus G35. G35 is 3. We get the value 8. So now we move to the next level. Next level we have subsets of size 2. There are 3 combinations and we find the value using the same recurrence. So first we have G234. G234. We write the expression minimum of. So first possibility, we move from 2 to 3. 2 to 3 cost is 4. 4 plus G. We arrive at 3. What remains is 4. Next possibility is we move from 2 to 4. So 2 to 4 cost, 2 to 4 cost is 6. Six plus G. We move to 4, remaining is 3. Now we put the values of G34 and G43. So G34 value is 7 and G43 value is 8. So we get this as 11 and 14. We get 11. Next sub problem is G324. We write the expression. This is minimum. First possibility 3 to 2. 3 to 2 cost. 3 to 2 cost is 4. 4 plus G. We move at 2. Remaining subset is 4. Next possibility 3 to 4. 3 to 4 cost is 5. 5 plus G. We move at 4. Remaining element is 2. Just put the values of G24 and G42. So G24 value is 8. And G42 value is 7. So we get the values 12 and 12. We get 12 as answer. Now the last sub problem is G423. This is minimize. So first possibility is 4 to 2 move. So 4 to 2 cost. 4 to 2 cost is 2. 4 to 2 cost is 6. 6 plus G. We move to 2. Remaining element is 3. Next possibility is 4 to 3 move. 4 to 3 move. Its cost is 5. 5 plus G. Uh, 4 to 3 move. Its cost is 5. G. 3. Remaining element is 2. Just put the values of G23 and G32. G23 value is 7. And G32 value is 5. So we get minimum of 13 and 10. So we get the value 10. Now the original problem we solve using the same idea. G of 1, 2, 3, 4. We write the expression, minimize. First possibility is move from 1 to 2. 1 to 2 cost, 1 to 2 cost is 1. 1 plus g, we move to 2, remaining elements are 3 and 4. Next possibility is 1 to 3. 1 to 3 cost is 3. 3 plus g, we move to 3, remaining elements are 2, 4. And last combination is 1 to 4. Last possibility 1 to 4. 1 to 4, its cost is 2. So 2 plus, we move to 4, remaining elements are 2, 3. Now we put the previous values. G234, G234 value is 11. 1 plus 11, 3 plus G324. G324 value is 12. And 2 plus G423. G423 value is 10. So we get minimum of 12, 12, 15 and 12. So we get the value 12. So 12 is the minimum distance traveled by the salesman. So, and we can also recover the optimal tour, what exact cycle is taken. Just simply follow the path of the minimum and get the solution. So so the salesman starts from vertex 1. Which choice out of 2, 3, 4 it takes? So we have to consider this, which one is the minimum path. So there can be two possibilities, 2 or 4. Why? Because for both 2 or 4 possibilities, cost is same, 12. So we can choose any one. Take for example, we take this 2, take this one. This means we are choosing this path. So for this, we have chosen this vertex 1 because we start with 1. For this, we have taken this vertex 2. So after 1, we have 2. Now after 2, we have to consider G234. Consider G234. This is G234. Now here also find the optimal path. Minimum value is 11. It is from the first choice. First choice means we are following this path. So we have taken this vertex 3. No, not 3. Yes, correct, 3. We have taken this 3. So after 2 we have 3. So after 3, what option we have? So again we have to consider this G34. So we consider G34. So here we do not have any choice. The only possible move is this 4. So here the problem becomes G45. G45 means from 4 move directly to 1. So this 1 actually means this problem I can write. This is G1 2 3 4. And next we take this 2 is represented by 1 to 2 path. So remaining problem G2 3 4. Next, for this 3 we take G34 path, and finally for this G45. So G45 means from 4 directly move to 1. So here we are getting our cycle 1 2 3 4 1. So we have found one solution, and that is from we can say in this given diagram it is in clockwise direction like this: 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So this is so in this problem we are given a undirected graph. So undirected graph means the distances are two-way. So we can also find the same solution in reverse direction, means we can also go from 1 to 4 like this, 4 to 3, 3 to 2, and 2 to 1. So this also we can find. So if you consider our original solution, we will find that we have two options: the original G1 2 3 4, here it is G1 2 3 4. So there are two possible minimums. So for first option we move to 2, for third option we should move to 4, so that this time this is our sub problem G 4 2 3. So we can also write like this. So our initial problem was G1 2 3 4. From this we get G1 to 4 we move. So sub problem becomes 4 2 3. So from 1 we move to 4. Now we have to see how we get minimum in G4 2 3. So we consider G4 2 3, G4 2 3. So G4 2 3 minimum is 10. So we take the second option, G32. G32 means we move to 3. From this it is G32. From 4 we move to 3. Now we should consider G32. So G32 we have only a single option, G32 move to 2, and sub problem becomes G25. So next problem is G25, and next we move to 2. Now G25, it means move directly to 1. So move directly to 1. So this is counterclockwise in the original figure, 1 4 3 2 1. Here we can compare this in reverse direction, in counterclockwise direction, 1 4 3 2 1, 1 4 3 2 1. So we get two solutions. So in general, for any undirected graph we will have even number of solutions, one in clockwise direction, other in counterclockwise direction. But for the case when our input is directed graph, we can have odd number of solutions, because if we change the direction, distances will change and our solution will change.